So in this video we're talking about infinite limits at infinity, and we've already looked at some of these when we talked about those limits where the numerator kind of won the race in the battle towards infinity, so the limit did not exist. But if the limit as x approaches infinity does not approach a finite number, it's growing or it's increasing or decreasing without bounds, we have what's called an infinite limit at infinity. So the definition of infinite limits at infinity, if we let f be a function defined on the interval from a to infinity, and the statement, the limit as x approaches infinity of f of x equals infinity, means that for each positive number m, there is a corresponding number n greater than 0, such that f of x is greater than m whenever x is greater than n. So basically this is saying pick the largest positive number you can think of. There's some large positive number, such as long as x is greater than the n, then f of x is greater than your choice of positive number. And there's a version of this for the negative infinity as well. It's just saying that there is a number such that your x would be less than some n. And you can also define this for as x approaching negative infinity in either direction of f of x. So you can kind of think your way through these. Okay, so you've got the limit as x approaches infinity of x cubed. If you take a really large number and you cube it, you're going to get a really large number. There's nothing that's going to limit this and cause it to not go to positive infinity. So that would be the answer there, positive infinity. In part B, you notice that you have the limit as x approaches negative infinity of x to the fifth. Now if you take a really large negative number and raise it to the fifth, you're still going to get a really large negative number because it's going to preserve the signs. So this one is going to be equal to negative infinity also. But if you take the limit as x approaches negative infinity of x to the fourth, and you are raising a really large number that's negative to the fourth power, it's going to turn positive. So this would be positive infinity as well. And just to kind of throw another example in here, if you took the limit as x approaches negative infinity of something like negative 3x cubed, so you take the negative number, you cube it, you get a negative number, but when you multiply it by negative 3, that becomes a positive. So this one would actually be positive infinity. So when you're dealing with these rational expressions, you want to be careful about this also. So in this case, my numerator definitely wins. I've got an m of 2 and I've got an n of 1. But I'm going to take a positive number, square it, make it negative, and then divide it by a positive number. So this is going to end up being a positive infinity. I'm sorry, a negative infinity. Okay. And there is another way that you could verify this if you're not really comfortable with that kind of logic. You could try long division on these rational ones where the numerator is higher. So I would take that negative x squared plus 2x plus 3, and I would divide it by x minus 1. So negative x squared divided by x would be negative x. I get negative x squared plus x. Change the signs. That would be x. That'll give me a plus 1. So bringing down my plus 3, I would have x minus 1. Change the signs, and I get a 4. So I could write this easily as that's equal to the limit as x approaches infinity of negative x plus 1 plus 4 over x minus 1. And this isn't exactly an x over c, but you can, I'm sorry, a c over x VR, but you can see if you take infinity and subtract 1, you've still got an infinitely large number. If you divide 4 by it, that's going to be a really tiny fraction. So this ends up being negative infinity plus 1 plus 0, or negative infinity. So that's another way that you could go through that. Or you can just use the rules and kind of work your way through the signs. So with this one, I've got an m here which is 2 and an n which is 1, so I know it's going to be plus or minus infinity, but I do want to work my way through this because this numerator is going to go towards positive infinity, but this denominator is going to go towards negative infinity. So even though I know it's going to be plus or minus infinity, in this case, because it's a positive divided by a negative, it has to be negative infinity. So that would be my answer for that example.